Hello, you all are welcome to this episode 6 of 3030 Eklavya program. Starting from 2000, we are doing this series 3030 STEM and 3030 Eklavya, and for us, it's an absolutely emotional journey throughout this 5 years. And this year, starting from 15th August, once again, we have come up with the new episodes of 3030 Eklavya program. I am Jay, and I am right now getting connected to you with from the campus of IIT Gandhinagar, where we run small lab named Center for Creative Learning. Somewhere around here we have our small lab named Center for Creative Learning. And before this episodes, we have also broadcasted 5 episodes starting from 26 January, and we have received so much overwhelming response from people all across the country. In fact, the first episodes was trending on the YouTube at a 26th number, which also shows that in the country like India, apart from cricket and Bollywood, if the content is engaging enough, the learning can also made exciting. And overall, we have received 5.3 lakh views for the 5 episodes we have broadcasted. So thank you so much for your support, response, and the activities which you have shared with us, broadcasted in the episodes. Once again, the try is to come up with similarly exciting and engaging activities for all of you. Across the country, I would say the Haryana has a lot more participations compared to other states. So as UP also have a greater number of participation also, and all across the country there are various states, teachers and students are watching these programs. Among the boards, CBSE teachers have the highest registrations, so as the Gujarat and UP, but compared to the CBSE, the state board participation is limited. So I would request all of you to also watch the program at your level and also share it among the group. For all the episodes we publish, the submission of homework is compulsory if you wanted to get the avail of certifications. And if you have already paid the certification fees, so then for this particular 5 episodes, you don't have to do it one more time. And today, the episode is about computers, and for that, I wanted to go back to the very first question of this program, which is about how many computers do you have at your home? And the responses or the options you have is, do you have only one computer, including the mobile phones and the other devices, maybe the 5 computers? Or you might wanted to say that you are living isolated and you don't use the computer at all, and you might wanted to say that me myself is the computer. So yes, of course, maybe you have maybe using the one laptop or the desktops, but mind well, even your iron or the fridge or the car you drive is having computer sittings inside that. In fact, any modern car would have somewhere around 50 computers. Often computers, by that we don't mean the one which has the screen and a keyboard and so on, but the heart of the computer is something called as a processor, often also termed as microprocessors or a microcontroller. It looks something like this. This is the heart. This computer chip you have is actually one of the computer, and this is the brain of the computer which we uses. And there are 50 such computers, microprocessors are sitting in the car, and so many in your home. So we are all surrounded with this computing devices. So we are using it so much, but the question is, how well do we understand the processes going at the background in this particular computers? So today in this episode, we will try to understand how this computer work using a weighing scale. So although these computers are able to doing so many complex tasks, but at the end of the day, it has a very simple computing powers. It can do a very basic arithmetic operations, and through that, but there are so many such that basic computing units, that's why it's able to do such a complex task. So similarly, we have a weighing scale which can do a very basic operations. You put the weight over there and it would compare these weights. That's the basic computing this weighing scale can do. But through that, we would try to understand how to deal with the computer, in the sense that whatever task we wanted to do, we wanted to give it the computer who is very good at doing the simpler but a repetitive task in an efficient manner. So how do we ever get our things done from the computer? The thinking process about the computational thinking we would try to understand from the weighing scale. Apart from that, what language we speak is basically a decimal language. We have 10 symbol 0 to 9, but the computer can only understand, it's a very foolish guy, he can understand only 0 or plus 5 voltage. So with our language, how do we deal with computer which speaks a different language? So how do we understand these languages? That is what we would try to explore in this particular episodes. And after that, we would also like to see how you can make your own computer, it has quite a limited computing functionality. So with different materials, in fact using this wooden sticks, using this pulley system, and with basics of electronics, how we can make our own computer. That is what this episode is about. And what I meant by a computer can do a very basic operations, for that I'll take you to this a very basic gate, which is a NAND gate. So what I have here is two switches which I can press, and which are my inputs. These two switches are my input, and the green light you see here is actually the output. So this is a NAND gate, the reverse of an AND gate, which says that if both the switches are off, then the green line, the output is 0, or any of the switch I press, the output would be 1. Even if I don't press the switch, then also the output is 1. So the computer have this binary logic, on and off logic, and this NAND gate what you see, these are basically also called as a universal gate. At a very atomic computing level, there are so many NAND gates sitting. Very simple computing it can do, but so many such gates combines together in order to do the complex task which many of us experiences and many of us do in our daily life. So before I start with the episode content, what I would like to start with is this question about, let's say I have this 9 identical weights. You might have seen this in Sabji Mandis, and the idea is that I have 9 identical weights except one has a lesser weight compared to others. It's a counterfeit. In order to make a more profit, you have cheated a bit, and one of the weight has a lesser weight compared to all the other ones. So, and I have to use this weighing scale in order to find my counterfeit weight. The question is, in how many minimum times I can use this weighing scale and find that counterfeit? That's the question for you. Once again repeat the question for you. What I have here with me is 9 weights, and you have to use the weighing scale. What you can do is you can put the weights over there and compare their weights, and the question is how many times I have to use this weighing scale in order to find my the wrong guy, and I wanted to do it in the efficient manner, and also we wanted to find it out in how many minimum times I can use this weighing scale to find my counterfeit. So one might say that seems like within the by using the weighing scale 4 times I can actually find that. That the thought process for possibly that could be, okay, I can pick it up the one weight and put it on the both the sides of the weighing scale and trying to compare their weights. Now the moment I put this, you can see this yellow side has lifted a bit, and this is our false guy. This is the counterfeit weight we are looking for. But we are so lucky that in the very first attempt we have found our counterfeit. But you are choosing the weights randomly, and in this entire process, assume that your luck is absolutely bad and you won't find your counterfeit so easily. Now once again, let me mix it up and repeat the same process. So I'll pick it up two of this weight randomly and put on both the sides, and you would say that they both are getting balanced. So we know for sure that these are not the counterfeit. So let me put them on the sides. Once again, let me pick it up the next two. Once again, they are balanced, so this can also be removed. Similarly, let me put the next two weights. These are once again getting balanced. So balance means they have the same weight and they cannot be the counterfeit. So I have used the weighing scale 3 times and 6 weights have been removed, 3 more to go. And once again, let me put these two over there. They are also balanced, which implies these remaining weight is actually the counterfeit. So every time I have put the 2 weights over there, there were total 9 weights. So after using the weighing scale for 4 times, I could find my counterfeit in a guaranteed way. The question is, can I find this wrong weight in a even more efficient way? Here I have used 4 times. So can I lessen the number of times the weighing scale I am using? So let me once again mix it up. So another possible approach could be, here we have tried to put it up the 2 weights, one weights in each of the sides. Can I divide this entire set into a half and put them on each of the sides? So I have divided the 9 weights into half of the size and put the 4 over here. 1 weight is remaining that I have left it here. Now there are 2 scenarios possible. One possibility could be that both of them are balanced. So in the very first instance, we would find our counterfeit. But mind well, we are not so lucky in this entire process. So the other possibility could be one of the side is raising, and that's where our counterfeit might lie. So let me put both of them and try to measure them. And you can see the yellow sides has lifted up, which means my counterfeit must be, my false weight must be somewhere around this 4 sets. So let me remove these 4 of the sets. So in a very first instance, using the weighing scale for using the weighing scale once, we have removed the 5 weights already. Now remaining 4 is divided once again into half set, and while measuring it, you can see that this has a lesser weight, which means my counterfeit must be among these 2. So we have used the weighing scale twice. There are 2 last remaining weights. While measuring it, now I have found my counterfeit, which is sitting on this sides. So you see, in this particular process, every time we have keep on having the number of sets I have. So in the initial, I have 9 weights which were divided into 4, and 1 were remaining. Then 4 were dividing further into half, 2, and the 2 were once again divided into half by 1 and 1. So in 3 instances, we have used the weighing scale for 3 times, and in this method, we are guaranteed to find among the 9 weights, we are guaranteed to find using this method our counterfeit by using the weighing scale for 3 times. Can we do it in even more efficient way? So what we have done is divided the entire set into 2 parts. Can I do it by dividing this entire set into 3 equal parts? And how can I do so? So I'll put the 1/3, one of the set on the left hand side, this red side, the another 3 on the yellow sides, and there are remaining 3 sitting over there. So now there are 3 equal paths, and let's once again try to measure the weights. Now once again there are 2 possibilities. One is both of them are balanced. In that case, my counterfeit must be on the remaining one, or either of the sides would be gonna lift it up. Then once again I can find which that set must have the counterfeit. Now measuring this, you can see this side has lifted up, which means in a very first instance I have removed the 6 weights which doesn't have my counterfeit, and among these 3 I have to once again find my which one is the fall guy. So once again I am dividing into the 3 equal parts. There are 3 weights. One I am putting on the red side, one I am putting on the yellow side, and the remaining one, let me put it over here, and let's try to measure them. And you can see that the red side has lifted up, and we have searched. We have found our counterfeits. So by using only twice this weighing scale, we have find our counterfeit. And you might be wondering about what it has to do with the computers. So computer regularly have to search from its database whatever data is looking for, whatever processing you are doing, whatever task you are doing. Computer has to from the large pool of data, it has to search for a particular data. That's what exactly we have tried to do here with the 9 set of weights, and for the comparisons and for the searching we have used our weighing scale. Here there were just only 9 set of weights. Imagine you have a huge database, or let's say for example a library. For instance, let's take an example of Nalanda University Library. In the 5th and 6th century, it's been known that it was world's largest library with having 90 lakh books in the library. And from that, maybe with using its name or a code, let's say we wanted to search a library. The question is, with these methods, how much time it would take to find a particular book. So let me show you the calculation here. So let's say there are 90 lakh books in the Nalanda University Library, and if I use the very first method, then it might take 2 months to find even a single book. Whereas if I find the second method of dividing the entire thing into the equal parts, then I would take 23 seconds, whereas the last method, which was dividing the entire data sets into 3 equal parts, then I might take only 14 seconds. Now you see, the very first method was taking days, in fact 2 months, and whereas the other methods were taking a few seconds, 24 seconds and 14 seconds and so on. So such a huge difference on with what technique you use for doing your search. And the computer is all about efficiency. We wanted to do our task quite quickly, quite fast, and so which technique do you use to search your data? That matters a lot, and a computer have to do it very constantly. In fact, when you search in a Google, so for an example, if you search 3030 Eklavya in a Google, among 12,000 search results, it has done in a very instantaneously. It has just done in a 0.15 second or so, and that it's able to do because of the very efficient way of searching techniques. A few such methods we have tried to do here in order to find our counterfeit coins along with the weighing scales. Also, just like searching, my data also has to be very organized. Just like in a library, you would see all the books are put in an order in a certain sorted way with either their number or some code, or let's say with their names. That helps you to find the search the book very easily. Similarly, this Google search technique also does the ordering of their database in such a way that the searching becomes very easy. Now for that, in order to, let's say for example, having the data sorted really helps. So question is, the same example of Nalanda University Library. Let's say there are 90 lakh books and I wanted to organize them alphabetically in an alphabetical order. Question is, how much time it would take for me to sort all the books in a Nalanda University? That's a question for you. repeat the question once again. What we are asking here is, the data, the sorted data really helps me. So now what we are trying to visualize here is, let's say in a library, Nalanda University library, we have 90 lakh books and we wanted to maybe sort them in an order, let's say alphabetically order or so. Question is, how much time it would take for me to arrange them? One option is that maybe 5 days, maybe 5 years, maybe 5 generations, or 5 yugas that you would take to sort them. And in order to understand this process of sorting or how much time it would take, what I have here is with me 9 a set of this small boxes which has coins in it to vary their weights. Now what I'll do is, one possible technique, so we would try to understand the process of sorting with the example of these dibbies, and all of them have a different weight. Let me, the one possible approach, and let me shuffle them to put them into a random order. All right, I see. Now one possible approach to arrange them in an sorted order by their weights, I would start picking any 2 of these boxes, and whomsoever has the lesser weight or whomsoever has the more weight, I would try to let them sit in this weighing scale, and the one with the lesser weight, let me remove it and put it on the side. So I would make sure that whichever has the more weight, let's say for example among B and F, the B has the more weight, so I would let it rest on the weighing scale and remove the other one. Similarly among B and G, B has more weight, let me remove the G. Similarly among B and C, B has more weight. Among B and A, once again, B has more weight. So, and lastly, the E also has the lesser weight compared to B. So with this entire process, among the 7 dibbies I have, the 7 boxes I have, the B has the most weight. And so I by using the 6 comparisons, I have used the weighing scale for 6 times and found my heaviest guy over there, and I'm putting there on the at the end. Now I have left over with the 6 dibbies. Let me repeat the same process among these boxes and find whichever is the highest among the remaining one. And for that, I would let the one with the more weight sit inside the weighing scale and remove the other guys. So let's say among the F and D, the F has the more weight. Among F and G, G has more weight. So let me remove the F. Then next comes C. C has more weight, so I will remove the G, and then once again C has the more weight. The last one is E, and it turns out to be C has the second highest weight in the entire set. So let me put it on the second positions. Now I've left over with the 5 boxes. Once again, let's start comparing. A has more weight, removing the E, removing this, removing the lighter one, and the last one is D, removing this. And I've got my third guy. And now let's once again compare this. Let the heavier guy keep on resting on the weighing scale. So I have got my 4th highest. There are 3 remaining, and so among these 3, F has the more weight, and among D and E, D has the more weight. So let me put it over there. So now you see all of them are sorted with their weight, and in order to conclude that, what we have done is, in the very first iterations, we have found our B box with the highest weight. And how we have achieved that? By using the 6 by doing the 6 comparisons. I have used the weighing scale for 6 times. For the C, I have to do the 5 comparisons and use the weighing scale for 5 times, then 4, 3, 2, 1. If I sum them up, I have used my weighing scale for 21 times in order to sort the 7 dibbies. There can be another interesting way to do the similar sorting method. So for that, let me shuffle them once again. Let me put them into a random order. And what next I will do, I will pick up any of the box randomly from this. Let me use this box G, and I'll keep on comparing the rest of the boxes with this. The one who has the more weight compared to G would go on the red side. The one who have the lesser weight compared to G will go on the green side. So let me start comparing them. This has more weight on the red side, less green side. F has a less weight, so it will go on the left. Okay. Then B has more weight, it would go on the red side. Then comes the A. Once again, A also has a more weight, so it would go on the red. And then D has the lesser weight compared to this, so it would go on the green side. So now you see all the boxes I have, the one on the green has lesser weight compared to G, all the red ones have more weight compared to G, so G would remain on the middle of the space. So, and these are of course not sorted among themselves. These are of course not sorted among themselves. We have found the position of G, and all I know is this have more weight compared to all of these guys. So now what process we have done here to find the position for G, we'll pick it up one randomly from this, and we'll repeat the same process once again here. So let me pick a randomly a D here. Whichever has the lesser weight would go on the left, whichever one has the more weight will go on the right. So let me pick it up the F, which has more weight, so I'll put it on the right. Then comes the E, that has less weight, so it will go on the left, and I have found my position of D. So now this set is sorted. The leftover is only this set. Let me pick it up one more time, the random guy from this, let's say C, and the one with the more weight will go on the right, one with the lesser weight will go on the left. So A has lesser weight, so it will go on the left, and the B has more weight, so that would go on the right, and the C is in the middle. So now this set is already sorted. This we have already done. G's positions we have already done, and now all the set is sorted. And how many times we have used the weighing scale? So you see, to find the position of G, we have done the 6 comparisons with all of them. For this set, we have done the comparison twice. So as for this set, so 6 plus 2 plus 2, 10 times we have used the weighing scale in this particular method. Previously, we have used 21 times in the method. In this particular method, we have almost saved half of our time, half of our usage of the weighing scales. We have done it in a much efficient way compared to our previous method. So, and computer, dealing with the computer is all about doing your task in an efficient way. So and if I try to compare at a huge scale, a large database, just like for example the number of books in the Nalanda University. So there, if I, instead of, here we have done this exercise with 7 DBs, if I take, let's say, 90 lakh of the database of what we have in books, number of books in the Nalanda University, and assume that here I am trying to measure the weight, there we are doing the comparisons with maybe their name or the code or whatever ordering we wanted to measure, and maybe 1 second for doing that each of the comparisons. So for me it would take 10 lakh years, not sure how many generations it would take in order to sort them all, whereas the second method would take 6 years, whereas this 10,000 years, 10 lakh years, whereas compared to that, the second method would take only 6 years. And so what we have tried to understand here is that in the computer, this searching for the data and making sure the data is organized keep on happening in the back of the process, and it has to do it in the efficient way in order to do it in the very fast way. That's the same exercise we have tried to do by using the weighing scales. So we are trying to understand the technology, we are trying to understand the computer, but without using technology, without using computer, using the weighing scale, we are trying to understand the same process which is going there in the computer. And of course, you can also try to do this exercise in your classrooms and come up with the different techniques of searching and sorting. Maybe you can make your own tarazu as well. You can make your own weighing scale. So here I have made out of an hanger, and two cups are hanging, and maybe you wanted to put your weights by inserting a different coins in a small boxes, and do share your photograph and video with us. There is another activity, interesting activity, which you can do at your places. Instead of the weighing balance, maybe you wanted to draw a chart like this, where in this pink boxes you see the square boxes here, where the students would stand with different number as a tag, and they would keep on moving in this chart. In the circular box, they would compare themselves. Let's say if it's a number, they would compare who is the lesser and who is the higher, and according to that, they would either go on the red. The bigger number will go on the red, the smaller number will go on a green, and after doing this process, at the output would be all students sorted. And very similar activity we tried with the kids. So what we have used is, we have used the electric tape to make these charts. You can also draw it using chalk, and you see the inputs were the unordered data, and the output it's ordered numbers. Similarly, you can use the higher digit numbers and try to do the very similar sorting exercise. Or maybe another interesting idea could be, you might wanted to compare your height for the sorting mechanisms, and you see the kids are all sorted based on their height after this particular process. And of course, this is for the 4 kids. Maybe you want to try it with the 6 kids or 8 kids, how the chart would look like this. This, of course, you can try it out at your place. Going ahead, so till now, what we have tried to understand, this computer who understands only maybe a limited operations the computer can do, but in a very efficient manner it can do. So whatever task we wanted to achieve, asking the computers to do, which could be based on the very limited operations. So how do we our work gets done by the computer by converting into a smaller operations? This thinking, this computational thinking process we have tried to understood by, without technology, using the weighing scale we have tried to understood that. And now going ahead, for that I would like to invite my colleague Shyam to come over stage, and here is the question for you. The question is, what do you think? What is the height of Shyam? Do you think that it would be a 69 inch? Or it could be 1000101 inch? Or it could be 2120 inch? Or it feels like our colleague Shyam is with the great personalities, and it's very hard to find its height. Yeah. So what do you think? Please do answer. Question once again. What we are looking at is trying to measure Shyam, and what do you think? What would be his height? 69 inch or 1000101 inch or 2120 inch? Or maybe it's very difficult to measure his height looking at the personality he has. Now, in order to measure Shyam's height, what we have here is the different length sticks with the length of power of 2's. So here I have 2 to the power 0, 1. Here I have 2 to the power 1, which is 2, 4, 8, 16, 32, and 64. So in order to measure Shyam's height, all I have is power of 2's. This is also very similar to a binary language. The numbers are represent all the power of 2's, and why so? Because our computer also understands in binary. Our language of the computer is also binary, and we will try to measure Shyam's height using this power of 2's. So here I have 64. Then maybe I can pick it up 4, insert here, maybe one more, and you see the sticks I have used here is only power of 2's, that's a 64, 4 and 1, so that's 69 each, but when I speak 69, that's actually in a decimal. So the language we speak, and for that maybe let me try to explain it in the iPad. So what I meant by 69, when you write 6 besides 9, so what process you do in the background, this 9 is actually multiplied with the 10 to the power 0. So the language we speak is actually a decimal. It has 10 symbols. It's a base 10. 0 to 9 there are 10 symbols, and each position is multiplied with the power of 10. So 9 is multiplied with 10 to the power 0. The next position is multiplied, that number is multiplied with 10 to the power 1, which is 10. So your 69, when you write 6 besides 9, that's actually 60 plus 9. And similarly, what we have tried to do here is, we have used only 2 symbols. We have used the binary language, base 2 language. All the power of 2's, and how it can be represented here is 69 can be written as 64, which is 2 to the power 6, 4, which is 2 to the power 2, then once again 2 to the power 0 is 1. Or I can also write it up as 1 0 0 0 1 0 1, which means this first position is multiplied with 2 to the power 0, which is 1. Just like in the decimal, we have 10 to the power 0 for the first place, similar, and that's because of it has base 10. In the binary, which is base 2, I have power of 2's. Similarly, the next position is 2 to the power 1, which is 2, and that's multiplied, 2 is multiplied with 0. Similarly, here I have 2 to the power 2, which is 4, and that's where it's 4. The next one is 8, then 16, then 32, and this one is 2 to the power 6, which is 64. Only power of 2's, in this 1 and 0 representations, in binary representation, it's all power of 2's being used to does the calculation. Very similar to what we have done to measure the height of sham here. Only power of 2's is being used. And why it is so important to understand this notion? Because we speak decimal language. We use 10 symbols. Very coincidentally, the fingers in our hands are also 10, and the computer, that only understands on and off, that only speaks the language of 0 and 1. It has only 2 symbols, 0 voltage and plus 5 voltage. So the translation from our language to computer's language, that keeps on going when we have to deal with the computer, and that's why it's so essential to understand the representations of a number. It's the same quantity. Shyam's height is a 69 inch, and similarly Shyam's height is also 1000101. Both of them are same, a different representation to show the same quantity. And this is the base 2. I can also do the same process, same thing in a base 3 as well. So for that, I have used the all the lengths with power of 3. So here I have 3 to the power 0, which is 1. The next I have 3 to the power 1, which is 3. The next I have 3 to the power 2, which is 9. The next I have 3 to the power 3, which is 27. And in order to measure Shyam's height, what I will do next is, I'll insert these two, and next maybe the 9. So 27 plus 27 is 54. Then I will maybe insert 9. Now this is 63, and maybe 2 3's, and now this is 69. And in other sense, what I can also write it up as is, this is 54 plus 9 plus 6. These are all power of 3's multiplied with the coefficient. So if I wanted to represent the same in the power of 3s, this is what it looks like. I can also say this 3 to the power 3, 27, there are 2 sticks being used, that's why 2 over there. For the 9, that's at 3 to the power 2, we have used only 1 stick of 9, that's why there is a 1. Similarly 3, there are 2 sticks of 3 length we have used, and of course we have not used the stick with the 1 length. So in some sense, if I call Shyam's height in the decimal, it's 69. In the binary, it's 10010, and in the ternary, in the base 3, it's 2 1 2, and we have not used 1, that's why a 0 here. So 2 1 2 0, it's also the height of Shyam. It's just a different representation for the same thing. So we have measure his height in base 2, in base 3. The base 2 is the binary language, the language which computer speaks, and it's absolutely essential because we have to deal with the computer who speaks a different numerical representations, different languages. So height has been measured in base 2 and base 3, and now what we'll do next is I have a big weighing scale over there. So we would request Shyam to sit over there, and we would try to measure his weight in base 4. So base 4 is basically all the one with power of 4s. And for that, let me have the safety gears. So what we'll try to do here is we would measure Shyam's weight with the weights with power of 4s. So here I have 16, which is 4 to the power 2. Here I have 4, which is 4 to the power 1. And here I have this tiny one, which is 4 to the power 1, 4 to the power 0 kg. So for that, to measure Shyam's weight, I would hang this 4 to the power 2 with 3. So the moment I hang it here, the 16 is multiplied with 3, and it becomes 48 kg. And now if I do so Shyam's weight is more than the 48 kg. So what I'll do next is I'll pick up this 4, which is 4 to the power 1, let it hang at 3's place. And now, previously it was 48, the 16 was multiplied by 3 is 48, the 4 is multiplied by 3, that's a 12, 48 plus 12 is 60 kg. So it seems like Shyam's weight is lesser than the 16 kg. So what I'll do next is I will let it hang at the 2's place. So this is 48, this is 8, this becomes 56 kg. Oh no, it seems like Shyam is even lighter than the 56 kg. So I would take this and let it hang at the first place. Now it's a 48 plus 4, 52 kg. Voila! And you see now the Shyam is balanced with the 52 kg on the sides. And if I look at it, the representation, so now I can also tell that it's basically the 4 to the power 2 is multiplied with 3, 4 to the power 1 is multiplied with 1, and 4 to the power 0 is not used at all, so it's multiplied with 0. So in one sense, it's a 52 kg in decimal, and at the same time, it's also 310 in base 4. So congratulations, Shyam, you have got your weight in base 4, you have got your height in the binary and ternary, and maybe his entire profile we'll try to uncover in this entire series. Thank you so much, Shyam, for being there. So if I try to summarize what exercise we have done here, we have tried to see that computer speaks a very different language. It uses a different numerical representations, and that's base 2. The language we speak is the base 10. It's a decimal language. So we have tried to do a measurement in a different basis. We have tried to represent the numbers in different forms and try to understand how to speak or how to deal with the computers. So that fundamentals we have tried to understand here as a part of the measuring exercise. What I wanted to show you next is, till now what we have seen that how to deal with the computer, how to get our work done with the computer, that thought process, computational thinking, the language it speaks. Now we would try to make or I would try to show you how to make our own computer using different materials. So as we spoke, the computer is made out of a very simpler basic logic. The NAND gate we have shared with you. So this has two inputs and this is the output. The logic it is whenever both the switches are pressed off, then or both the switches are pressed on, that's the only times when the output is 0. So it's a reverse of an AND logic, where both the ones would give you the output as 1 in the AND gate. It's a reverse of that. So only with the two ones it would get off, just like this. So for 1 0 as the output is 1. For the 0 1, when I press this key, that's the off, that's a 0. That's also the output is 1. It's the only time when both of them are pressed. That's one state. My mistake on the previous occasions. So now both of them are pressed. It's a 1 input and both the inputs are 1 and the output is 0 in this case. Now only this is the logic gates. It's called a NAND logic gate, and the computer is made out of so many such gates. And what I wanted to show you next is we have arranged the wooden pieces here, and this is my AND gate. What I meant by an AND gate is whenever both the inputs are 1, then and then the output would be 1. So here in this particular arrangements, if I make this guy fall, then it's interpreted as 1. Whenever it's standing, it is interpreted as 0. These are the two inputs, and here the white blocks are the output. So if it's fallen, that means the output is 1. If it is staying over there, then output is 0. So what I'll try to illustrate you here, let me press either of the guy and giving the input as 1 and the next input as 0, and let's see what happens. And you see that these white blocks are standing as it is, which means the output is 0. So if only one is pressing, only the input is 1, the other input is 0, then the output is 0. Here I have the similar gate, the arrangements, a very similar arrangements. Now here I would try to give both the input as 1. I'll try to push both the sticks at the same time, and hopefully the output should be 1 over there. And let's try to see what happens if I press both of them together. And you see the output is 1. So this is my AND gate. We have tried to made it using this wooden blocks. What I wanted to show you next is that using similar blocks, I can actually make a computer. So what we have seen here is the AND gate, the arrangement of this wooden block, which says that the output is 1 only and only if both the inputs are 1. Only and only you pressed or these wooden blocks and letting them fall, then the inputs are, both the inputs are 1, and only then the output would be 1. That's the AND gate. Similarly, I have another gate called XOR gate, which means if either of them is 1, if either of them is falling in the input, then the output would be 1. The output blocks would also fall down. By using only these gates, the first year students, as a part of IIT Gandhinagar Foundation program, made a calculator, made an adding machine. So in the input, they have given the 6 and 5 as the inputs, and in the output, the 11. The output was 11 in this particular wooden block machines. And how come they have given the inputs? Mind well, it's the computer's language. So they have given the input in the form of binaries, 1, 1 and 0. They have tap in the positions for 2 and 4 in the one of the input size, and they have also tap in the 4 and 1 for the input size. And in the output, you would see that for the 1, 2 and 8, these are the block size in the output. They will gonna fall down. Let me play the video for you. So here they are tapping in for the input wooden blocks, and in the output you would say that 1, 2 and the 8 rows are falling down, which means the output is 11 for 5 plus 6. And of course they are thrilled to look at their outputs. So a computer a basic computer made out of this wooden blocks. Similarly, I wanted to show you another interesting computer. That for that, let me put this table in a side a bit. So here I have a computer made out of pulleys. So this is my output ring. So let's say, for example, the level of it, the height of it, which will tell you whether the output is 0 or 1. So for an example, when this particular ring is at this particular height, when it's lifted up, this is where the output is 1. When it is on this particular position, that's where the output is 0. And similarly, here I have two smaller rings, which are basically the inputs. So whenever they are up, that's the 1, and whenever they are on this positions, on the lower positions, that's where the output is 0. Now this is the NAND gate, a very similar gate what you have seen previously, where both of them are 1. That's the only scenario when output is 0. On either of the occasion, the output would be always 1. So let's say when both of them are 0, the smaller rings, the input rings, are at the 0 position, the output is at 1. Let me put one of the ring on the 1, and you would see that this is the, let's say for example, 1 positions, and you would see that still my output is 1. Let me put the another one, this ring, on the 1 positions, and you would see the output is still 1. When I make both of them, both the rings at 1, you would see that output is now 0. That's the only scenario where the output is 0. On all the other scenario, the output was 1 only. So this is a NAND gate using a pulley systems, and what I wanted to show you next is you can also once again made a computer, adding machine out of this pulley systems. Let me play the video for you. Here you have. So I wanted to make a half adder. What I mean by an half adder is, in the input you have just like the binary language computer speaks, the on and off, the zeros and 1. You can either give the input as 0 on the one input, on the other input once again you can have 0 or the 1. So for the two zeros, the sum would be 0, the carry is also 0. Similarly, when you have 1 0 or 0 1 as the input, the sum is 1 and the carry would be 0. When both of them are 1, the sum is of course 0 and the carry is 1. So the same logic we have tried to implement, the adding machine for the two bits, we have tried to implement it using pulleys. So whenever the input is 0 0, the output is also 0 0. Whenever one of them is given as a 1 input, you would see that the sum is at 1 and the carry is of course at 0. When both of them are 1, you would see that the carry is 1 and of course the sum is 0. So the heart of the computer, the gates, the basic computing functionality, we have tried to implement it using different ways. You have seen how using the wooden blocks you can make the logic gates. Using pulleys you can make these logic gates, and combining them you can actually make adding machine, simple adding machines we have tried to make. What I also wanted to show you here, what you say are the clocks made out of a basic gates and electronics. So what you see, this entire portion is basically a clock, where these are the basic electronics, basic gates. In fact, you can see here, let me try to balance this for a bit. Okay. Now the block you see here, these are basically basic gates being made in order to let this particular 7-segment display run, and this entire thing has been combined into this smaller black computer chips you see over there. They has embedded entire thing into this very small area. Now similarly, this entire small area has been embedded into the smaller portions, and similarly this entire things has once again made compact in order to make it more and more compact. So the moment you try to keeping more and more compact, That's how you are trying to reduce the overall size of the computer chips, and eventually everything is been embedded into such a small size computer chip like this, and none of them has computer being implemented. The entire clock is made out of this basic electronics, the basic unit you see over there. Similarly, what we have tried to make here is a computer which can play a Tetris game. In the childhood, you might have played this game where the blocks are coming, and you can maybe slide them, or maybe you can rotate them and play the game of Tetris. So that game of Tetris we have tried to implement it here out of the breadboard. So it's a computer over a breadboard, and very soon we are trying to launch the program on how to create such computers using basic electronics, which would help us trying to understand this technology which we used every day. So once again, let me try to talk about or summarize about what we have talked already. And we have done so many activities. We have tried to sort the weights, the boxes, and using the weighing scale. Similarly, we have also done the sorting activity by drawing a network on the ground and trying to understand how computer manages its data. We have also tried to make computer using different materials, using pulley, the mechanical pulleys, using wooden blocks. The same thing you can also do by putting the playing cards over there and trying to understand how the computers is actually working. We have tried to open up the computer and try to see inside the basic functionality of these computers. And yeah. So thank you so much for being connected for the entire hour. And on the next episode of the Eklavya we would be launching on 24th of August on Sunday 4 p.m. So hoping to see you over there live 4 p.m. on the 24th August Sunday. Thank you so much for being the a part of the program, watching these programs. And in order to get the certificate, homework submission is necessary. So here you can go on the 3030 Eklavya web page, and you can also search on this tiny URL link to submit your homework, which is essential to get the certificate. Thank you so much for watching this episode.
Hi guys, back with another video with new stage, new people.
Hello everyone, we have made a domino adder. So it is a calculator which uses two 3-bit inputs to give one 4-bit output. It consists of one half adder and two full adders.
It's made up of various logic gates which we built using Dominoes, like this XOR gate, AND gate, and this OR gate.
Now we are going to add 5 plus 6, which will give us output as 11.
It has taken us 4 to 5 failures and more than 15 hours at least. Today we've been working for 5 to 6 hours at least.
It's 3 AM right now.
At IITGM, creativity meets science in the most unexpected ways. Students have crafted an extraordinary portrait of Dr. Vikram Sarabhai, the father of India's space program, using nothing but natural stones in varying shades. Each stone was carefully chosen and placed to create depth, light, and shadow. No paint, no pixels, just pure precision. Vikram Sarabhai laid the foundation for ISRO, envisioning a future where India reaches for the stars. And today, these students pay tribute, blending art, innovation, and admiration into one powerful creation. Tribute to a legend made of stones built with vision.
क्या बात है, 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 क्या बात है। फाइनली कितना बज रहा है? 1:15 बज रहा है यार, 1:15 बज रहा है। ऑल राइट, नो फाइनली दिस इज अमेजिंग कि ये हमारा जो लोग को वीडियो बना रहे हैं उसके लिए दिखा देते हैं। ये हमारा क्लॉक मॉड्यूल है, यहाँ पर मैनुअल भी है और बटन दबाकर भी है। कल गलती क्या हुई थी गौरांग भाई, अगली बार से सोल्डरिंग ढंग से करेंगे और आउटपुट इनेबल हवा में नहीं छोड़ना है उसको। ट्रांसीवर का इसने आउटपुट इनेबल हवा में छोड़ दिया तो 3 घंटे लगते हैं। इट्स जस्ट फिनोमिनल। थैंक यू, मजा आ गया।